Presenting this before at Russian Dev Club in Tallinn, so that's my second try. And I will talk today about a bit about big data in general, a bit about Hadoop, and a bit more about Spark and what it is. So, how many of you know what's a big data? Alright, so good, healthy 20%, nice. Who knows what's Hadoop? Actually, people know more about Hadoop than big data. Very interesting. And Spark? All right. So unfortunately, I don't have any cat pictures. But yeah, so if you open Wikipedia, then you'll find out that big data is defined in terms of either volume, variety, or velocity. So basically, volume means that you're working with lots of data. You can train more complicated models with more parameters. You get more predictive ability. Variety means that you can work with very many different kinds of data. Typically, like in large organizations, there is large variety of different data formats, data sources, and so the better you can work with them, like the more big data you are. And finally, velocity is about how fast you can process messages and respond to them with something smart. So you can detect events, or you can present some dashboards, and so on. So I will be mostly talking about the volume and a bit about velocity. And so just to clarify the definitions, if your data fits into 1 terabyte of RAM, which apparently is the amount of RAM which PhD students in Stanford have, or then basically this means you don't need big data. You actually need a small data. Okay, I realize I'm showing you the old version of the slides, but hopefully it will be okay. And in this case, actually, your tool stack will be Python. Python is slow, but for this reason, most of tools for Python are written in C++, and Python is just a small wrapper around it. That's why actually many data scientists use Python and NumPy and so on, scikit. And so I would actually suggest to use it as a default. Well, there are some other options like R or MATLAB or Julia. And then in case you actually have like tens or hundreds of terabytes of data, up to petabytes, apparently there are organizations which have tens of petabytes, and you need to do processing on 10 or more computing nodes, then you should consider actually big data tools and approaches. So Hadoop was like the first generation of such tools. It was built on top of, or modeling the ideas of Google, Google File System, Google MapReduce, and Google BigTable. And then about 5 years ago, a project called Spark was started. Largely, they just looked at large Hadoop distributions and installations, and looked where are the problems, and tried to solve them. Also, what happened is that hardware has changed a lot. 10 years ago, RAM was expensive. Now, well, the amount of RAM you have in a cluster is huge. And so the big difference between Spark and Hadoop is that Spark tries to optimize in-memory computation, so it keeps data in the memory. Well, let's see how old my slides are. But anyway, so some examples of what you could do with big data analytics. So, well, the most typical example is business intelligence, which is mostly about mining logs of transactions, or somebody clicked on something, or some messages, emails. And the most typical tool here is basically analytical SQL. So it's like SQL, but not for updating like 2 or 3 rows, but actually doing big queries involving lots of data, aggregating, filtering, grouping data. So then there is something called sentiment analysis, which is basically trying to infer the emotion of the person who wrote a text. So you see a movie review and it says that this movie sucks. So you should infer that the person didn't like the movie. Or like the opposite, this movie is fantastic, and so you then try to infer that the person actually liked the movie. And well, obviously, like there are more complicated models of how people feel different stuff, and you can try to infer that. Like, I don't know, sarcasm and so on. Lots of fraud detection. So for instance, spam. So basically you get emails, you need to understand who of them are selling you Viagra and who is trying to talk to you about work. Credit card fraud is basically understanding transactions made with stolen credit card numbers. Various recommendations, typically of music. So for instance, like some application knows that you listen to some music, and it can predict what other songs you will like. And the same thing works for products, like for instance in Amazon, like it knows what you bought before, it has seen many other people what they bought, and it can infer what you might be interested in. So they will suggest it to you. I'm sure you have all seen it. Then there's stuff like graph analysis. For instance, PageRank is this classical algorithm of Google, which they use to identify how important one web page is compared to the others. Admittedly, actually, Google uses like 100 different signals to combine ranking on the page, but one of them is PageRank. So it's a bit of a PR thing, but it's definitely also very cool. And in general, search engines, they work with lots of data indexed from the World Wide Web, and well, there's lots of data, you need to process it. But apparently, yeah. Now we have a brief overview of what's Hadoop. So Hadoop is mostly Java-based implementation of some ideas which came from Google. So maybe at the core of it is something called HDFS, which is a Hadoop file system. And so essentially it's a file system which works on like clusters of computers. Files are split into large chunks, like let's say 110 megabytes. And you can append to files, but you can't really overwrite the files. And generally you're expected to like process big chunks of data at a time. And what it does, it replicates these big chunks in, let's say, 2 or 3 computers. So if one of them dies, your data remains intact. And more importantly, you can ask on which computers your chunks are located, and you can schedule your computations on the computer where the data is. Thus, you achieve data locality, and you don't have to move data around the cluster, which is a very nice optimization. So below HDFS, there is a bunch of infrastructure services. So there are various schedulers of CPU and RAM and hard disk space in a cluster. So you can ask, give me 10 containers on these servers with, I don't know, 10 cores and, I don't know, 10 gigabytes of RAM. So it's a bit like, basically, like on each computer you might get Docker instance, but like you can do it in the cloud, basically. And below that there is a coordination service, well, it's called Zookeeper, and you can basically think of it as a distributed log service. What it means is that, let's say you have 5 machines running the Zookeeper. If 2 of them die, basically you will still have a consistent understanding of who is locking what, and you can basically use it for various services to coordinate with each other in a consistent way and reliable. So above the file system there are computation layers. So the first one was MapReduce. I haven't asked, how many of you know MapReduce? Cool. And so it was like the first generation thing, and then there came Spark. Tez is a bit similar, and actually the new project from Europe is called Flink. It's not very popular yet, but well, who knows? They have some good ideas. Then there is a bunch of different key value stores. So HBase is the one in Hadoop. It's basically based on the ideas of BigTable from Google. And Cassandra is essentially based on the ideas of Dynamo from Amazon. And they basically make different trade-offs in terms of consistency versus availability. In HBase, if your cluster is split in 2 parts due to network partition, it will stop working. In Cassandra, if it splits into 2 parts, you can basically keep writing into both parts, and it will basically merge your results after the cluster heals. But this means that temporarily you'll have inconsistent results, like you see something in one partition which you don't see in the other. And that's actually kind of like theoretically impossible to achieve both at the same time. So if you want to tolerate partitions, you'll have to be either consistent or available. And so, well, basically, HBase is consistent and Cassandra is available, or something called eventually consistent. So if the cluster heals, then eventually you will see a consistent view of data. And then there is a bunch of query engines which basically allow you to run SQL on top of data stored in HDFS in various formats geared for such analytics. Hive was the first of them. So essentially it allows you to run SQL queries on large files which are partitioned by some key, like time, ranges, and so on. It basically compiles the SQL into MapReduce commands, And it's not particularly fast, but it can actually has been used with petabytes of data. So, I mean, if you have 1 terabyte of data, then Hive will be painfully slow. Then there is Spark SQL, which is basically they use Spark to implement SQL. And when they released that, it was about 5 times faster than Hive. Obviously, Hive has learned from them and they have improved, but let's say 3 years ago, they were like much, much faster. Then Impala is another tool which is actually written in C++ and actually also modeled on one Google system. I think it's called F1. Yeah, and there is also Stringer and another drill. But, well, the list is long. And so I will be mostly talking about Spark, but I will also show you in general terms how MapReduce works. So imagine that you have an input file with a bunch of texts, and imagine that actually it's a very, very large input file, and different parts of this file are located on different cluster machines. And you want to compute for each word, like how many times this word occurs in that text. And obviously, like that's a very simple example. It's probably not what you will be solving in real life, but it's, I think, a good example to illustrate how MapReduce works. So what happens is that your file is split into pieces which are stored on different computers. Then the mapping phase happens. It's the first blue line here. And what happens is that each mapping phase, a task produces a bunch of key and value pairs. In this case, keys are basically the words, and the values are ones, but it can be something else. And then the shuffling phase happens. What it does is basically sorts these key value pairs by key, and let's say all pairs of key values with the same key in the end appear on one computer. It's done kind of like using hashing and sorting. But in the end, what happens, you get on each computer, let's say for each key, there will be one computer which contains all the values, and then you can apply a reduce function, which for each key will combine these values and produce some output. So in this case, you basically, let's say you see bear 1 2 times in the shuffling phase, and so the reducing will add up these ones, and it will say that the bear appeared 2 times. And then in the end, this result is, well, gathered together and probably saved again into HDFS, and you will have word counts. And this very simple idea allows you to actually express very complicated different algorithms, not extremely efficiently. Like if you are really trying to implement a custom algorithm in C++, you can do much, much better, like probably 10 to 100 times better. But, well, you have to be also expert in basically everything, distributed computing, machine learning, I don't know what else. And that's a generic framework which allows you, well, let's say at the time allowed you to be more productive than, let's say, C++ programmers. Time has passed, and by now, actually, I would say MapReduce is not very productive compared to Spark, for instance. In my personal opinion, like Hadoop and MapReduce is a bit like J2E 10 years ago, and Spark is a bit more like Spring, if you remember these old times. So that's the difference, like how much plumbing you have to do, like how fast response time you get. So when you run MapReduce queries, well, basically 5 seconds is minimum. Just empty query into cluster will take 5 seconds, which is not very fun. And Spark basically does it so that you can get for empty query response time in about 100 milliseconds, which is like below the psychological limit, so which is nice. And so, yeah, the problems with MapReduce is very verbose. It has high overhead of starting jobs. Then many real-world computations really consist of sequences of MapReduce jobs, like often in a loop. But what MapReduce does is that after each iteration of MapReduce, it saves everything back to disk, which means that even if your data could have fit into RAM of your machines, it will be written to disk and then read in again, which makes it extremely slower compared to the case where you could actually keep it in the RAM. And so that's one place where Spark really shines. Yeah, and well, basically that's what it says. And so what Spark does is that first, productivity, well, I would say you could basically write your programs in, let's say, 10 times less code. And the way you express it, you can write it in Java, but I would really suggest to do it in Scala, in Python, or Python. So it's really like you have to think it about this as a graph of functional transformations, but it's not as hard as typical functional programming language, so don't get scared. Like, no monads are required. Yeah, and what it has is that if you know Python or Scala, they have this command line. Well, basically, it's called a REPL, read, eval, print loop, where you can type in something and you get immediately the result. And well, this allows you to be very productive and well, test your things fast. And like I said, the second difference is performance. It could be in certain cases up to 10 times faster than MapReduce. And what happens is that it keeps the data in memory when it can. It tries to optimize the computation graph to basically to pipeline things and so on. I'll actually show how it works roughly. And yeah, so one very nice thing is that once you start a Spark context, within that Spark context, starting a task takes like 50 to 100 milliseconds. So you can be, well, you don't have to wait for a long time. And well, that's how it looks in Spark. So that's the program, this word count program written in two languages, in Scala and in Python. Well, what I should really tell you here is that the first line, well, basically creates something called RDD, which is a resilient distributed data set. And it trades in the data from HDFS, and essentially all your transformations happen in terms of RDDs. I'll again show you exactly what it is, but basically your file is an RDD. Then you apply to this file something called flat map, which does exactly what the picture showed. So it basically, for each line, produces a bunch of these key value pairs with like word, comma, 1. Well, then these, yeah, so there are a couple of two stages, which ends with reducing these values by the words, and the result is a word count. So it's extremely short program, and the Python version is very similar. And that's how it looks in MapReduce. So, well, that's in one language. Like 5 lines, 30 lines. Let's see. So, any questions so far?
You mentioned that once you boot up Spark context, then you don't have to. Then you can execute queries relatively faster. Mm-hmm. There are probably sometimes some situations when you have to reload it, like you altered the database scheme or whatever. What are those situations? When do you really need to reload the Spark context?
Mm. So generally, they actually try to enforce that you have one Spark context per GVM. So as long as the application runs and nothing tragic happens, you can reuse it forever. And the way generally big data works, there are no fixed schemas. So it either tries to enforce schema on the fly, or you can always change the schema. So there is really no need to, well, reload it. And yeah, the way actually Scala REPL, this eval loop works is that it will compile your small pieces of code and then ship that class bytecode to their, well, machines.
Mm-hmm. Yeah, with Python it will just interpret it.
Yeah, but it also actually manages to serialize the closures and send it. And the nice thing about Python is that, yes, it's slower, but it's still not that terribly slower because, let's say, how to put it, they try to batch operations together, so and that amortizes like the overhead of calling the Python function. There is some black magic inside this, but I mean, actually, like compared to the main Spark, it's not that hard. It's just lots of small hacking.
So we heard that if you talk about JVMs, then you can reuse the context as long as JVM instance lives.
Yeah. Yeah.
Okay. Thank you.
Yeah. So Spark. Spark consists of the Spark core, which is the main execution engine. It works on top of these schedulers, either Yarn or Mesos, or it has one of its own. And on top of Spark core, there are relatively small libraries for implementing Spark SQL, Spark streaming for processing data in real time. Real time in case of Spark means seconds, But, well, given that actually the one task scheduling overhead is like 100 milliseconds, what it does, it processes basically, let's say if typical Spark is batches, you take, like, I don't know, 10 terabytes of data and you spend the next minute processing them. And what Spark streaming does, it takes smaller batches of, let's say, what data came in the last second. And as long as it can process it in 1 second, it can keep up with the incoming messages. So it's not a true streaming platform. For instance, Flink does it better. And probably on Java, like if you're okay programmer, you can push it to 100 milliseconds. And if you're really good, to 10 milliseconds. But yeah, Spark basically streaming will not work below 1 second. Its main advantage is really productivity. You can prototype things fast, like you can redeploy them easily and so on. But yeah, if you want to have some very low latency, then, well, eventually you'll have to go to C++ and then maybe FPGAs, but that's a whole different story. There is a machine learning library which implements various machine learning algorithms using Spark. And there is also a library for graph processing. And, well, truth to be said, like most of these libraries are a bit slower, like 2-3 times slower than specialized counterparts. But they are relatively small pieces of code running on top of Spark core. So if you need to be productive and you don't really care like how much hardware you need to spend or rent on Amazon, then with Spark you can do it pretty fast and you can prototype things. Then if you really like have to push it like in terms of hardware utilization, well, maybe you have to use some specialized thing. But in most cases, that's probably not your biggest bottleneck. Like your biggest problem is probably speed of delivery, right? So like solving problems fast. It doesn't matter if you pay a bit more. People maybe are even more expensive than hardware in the end. Yeah, so well, that's the general structure of Spark and maybe a bit of philosophy behind. Yeah, so questions so far? So that's how the computation graph looks like. So what you see here is first is RDDs. These are these data sets. And the data set, resilient distributed data set, is basically a sequence of values, but they are partitions into pieces, and each partition can live on a separate computer. It doesn't have to, but it can. And they try to keep partitions in RAM. And typically, like what you do is you do partitioning on a key. So for instance, hash partitioning or range partitioning. And what you see next is that, so this gray thing is RDD, for instance, RDD-A. Then the blue things are partitions. And the arrows between them are data dependencies. So for instance, on top there, the blue partition of RDD-B is computed from the first partition of RDD-A. And so importantly, there are also either narrow or non-narrow dependencies. So if you look here, so given that RDD-E essentially is partitioned on the same principle or the same key as RDD-B, it can do narrow dependencies. While here, each partition has to take something from each of the other partitions. That's basically essentially the same thing as reduce in MapReduce, and it's done using similar ways, basically a shuffle. And again, Spark, what it tries to do is when you try to join, what you see essentially, that's a SQL join. Like you're joining two lists of data using some key, and if these two RDDs were partitioned on that key, then you will not have to shuffle. You can just copy data together. While, well, if you're unlucky and you actually have to repartition on a different key, then you'll have to do the shuffle, and well, that's the expensive part, essentially no algorithms. That's the nice picture. Did anybody understand anything from this picture? Okay, nobody, great. No questions? Okay. And so what Spark does, it takes this logical view of the program. So just to clarify, so imagine that you first had some input file, and then you apply the map function, if you remember the program. It produces a new RDD, and then another map, a new RDD, and then you join it with another RDD. So just to remind you, well, here is the Spark program. So essentially after each step, the output is an RDD. But the thing is that actually Spark does not immediately start the computation when you write this program. It will actually start the computation only when you force or collect the result. So it's a lazy computation. So actual computation will be scheduled only here, because by then it knows the whole computation graph and it can do optimizations.
What does the resilient mean, or what does it like?
I'll come back to it. But basically the idea is that the whole trick about Spark is that the way partitions are computed from the previous partitions is deterministic, which means that if you lose a partition, you can recompute it from the inputs. So what it does, it tries to keep partitions in the memory, but if some computer dies or you just have to swap them out, it's not tragic. You can always recompute it. So that's the way, that gives you the situation where you can keep computing while the checkpointing happens asynchronously. And that's another thing for performance.
So the data is stored in memory, but the query or the function is then stored on this end, because that needs to be restored in some kind.
Well, what happens is that typically you have a Spark context which has a Spark driver, and it contains the actual computation graph. And it tells, the nodes what to do. There are some more tricks, like there is a special cluster file system called Tachyon, which does the same thing but even cooler, but it's a separate topic. They apparently raised $10 million. I'm not sure how they will earn money, but go figure. It all comes from Berkeley, by the way. Yeah. So once you actually start executing this thing, an execution plan is created. So it's not very different from what happens to SQL. You write SQL, and then the optimizer analyzes your SQL and creates a plan. Well, truth to be said, SQL optimizer does two things. It first has logical optimization and then physical plan. There is no logical plan here. It's just a physical plan. So it doesn't reorder your computations. SQL basically can reorder your joins, for instance, if it thinks it will be more efficient. So this is something for the future, like logical optimization. But what it can do is create physical plan where, if you see here, these partitions, like this one depends on this one. So there is no point in moving it between different processes, different computers. So you can pipeline the computation by creating these pink tasks, where a bunch of sequences of RDD partitions are computed just on the fly. And it just produces the output. So in the end, what happens is that the computation is expressed in terms of tasks, and they can be larger than one RDD partition. It can pipeline multiple dependencies. And in general, it happens also in stages. So, this is one stage. This is the other. They can happen in parallel. When they are done, you can start this stage, which does the shuffle. And so what it achieves with that is that, in principle, if your computation is just a sequence of RDDs which are partitioned on the same key, you just give the input, and no data will be moved around between processes, just every process takes the input and produces the output for that partition. So that's a nice optimization. In MapReduce, you will be after each stage, writing to disk, reading in, doing computation again. So pipelining is the classical trick of any kind of software optimization.
So it's like the concept of lazy evaluation. So instead of keeping the value in mind, you keep the function in mind, and you only trigger it on demand.
Yeah, and when you trigger, actually, it creates the computation graph. And then it actually creates an optimal execution plan for this computation graph. So it tries to put computations together if they, logically fit together. And it's more efficient. Suppose that these pink things stopped here, then in the worst case, you would have to move data from here to the next machine. So that's expensive. But pipelining, you can avoid that. And so the resilient distributed data sets are read-only collections of values. They are partitioned across machines, typically on a key, hash partitioning, branch partitioning. But basically, for each key, you have to tell which partitions it belongs to. There is a bunch of transformations on these RDDs. You have actually seen them: this map, filter, flat map, join. If you know functional programming, it should be really obvious. If you have seen list comprehensions in any language also. And well, it's very similar to SQL. Like joins are in SQL, and well, map is also in SQL, and so on. So it's very similar. And then there's a bunch of actions like collect, save, or reduce, which actually will force the computation and then produce the output into like HDFS or somewhere else. So the thing is fault tolerant, which really means that given that the partitions are computed deterministically, so if you compute them twice, the result will be the same. You can be very loose in terms of keeping your intermediate outputs. You can just forget them and recompute if you're unlucky. And that basically enables you to optimize your usage of memory and not to wait for checkpointing, so you can continue computing. So it generally tries to partition the cache partitions in memory. There is certain caching scheme, like the most recent partitions are kept in memory. You can also tell it that if the partition doesn't fit in memory, please save it on disk, just as an optimization. But it's not necessary, strictly speaking. Any questions about that?
You said that the data is usually partitioned by ranges of the key or by hash value of key. Is there anything else you can partition them by, and why would you do that?
Well, yeah, I have never seen any other partition. But in the end, you really just, for each key, you have to compute some function which gives you a unique identifier of a partition. How you do that, it's up to you.
It has to be from the key, there's no other way, otherwise you cannot combine them.
Well, technically it can be from the whole record. But usually what happens is that you have a key and a value. But yeah, technically I don't think there is even separation between key and value. So. But you have to understand for each record which partition it belongs to. That's it. And yeah, any more questions? No? Okay. So, I had this nice slide about columnar file formats, but these are old slides. Anyways, so Hive on MapReduce. So Hive is this data warehousing system, and what Hive does is that it allows you to run big analytical SQL queries on long collections of data, typically logs or tables, and you can compute, I don't know, give me average price or something like group by country or something. And the amounts of data it works with can be terabytes, can be actually petabytes if you want. So you probably know that there are these transactional databases, OLTP, online transactional processing, and there are OLAP databases, which is online analytical processing. So OLTP databases is basically mostly about, if you have a website or a bank, some transactions come in, you have to update something, maybe add a field here or subtract there, and then maybe send a message somewhere. So each transaction is short-lived, but it has to be reliable. And well, I guess in the end, for OLTP databases, the performance is measured in terms of transactions per second, and there are scary benchmarks which do that. So OLAP databases are not meant for such cases, they are meant for data warehouses. So every time something happens in your organization, you create a record, this record goes into some queue and then saved into some kind of, well, essentially table. And you get a huge table of, well, everything that happened in your organization, and then hopefully an analyst can analyze this table using SQL and find something important, like, I don't know, people from Thailand don't buy cat food. Then can try to find out why. And so what they optimize for is inserting large chunks of data, not small chunks, and processing also large chunks of data. And very often this actually leads to the fact that the data is organized differently. So in transactional databases, typically you touch a few rows. And for this reason, if you think of a table, then each row is stored separately, like somewhere on disk. While for analytical databases, very often what you care is that you have these records, and they have hundreds of columns, for instance. But for this particular query, you really care just about 3. And you would also like to compress the data. And what they do is they store each column of the table separately. What it allows is to first query only the columns you need to read them separately. And second, what it allows you to do is to do much better compression. Because if your column is just, I don't know, birth date, you can compress it very well because it's just a sequence of birth dates. While if you store it row-wise, your compression will be much more challenging or expensive. And so that's the main thing about columnar file formats. And if you do any kind of analytical processing in big data, either in data warehouses or in Hadoop, then probably your data will be in columnar format, or it better be. And so in Hive there is something called optimized row columnar format called ORC. I think actually now the cool thing is called Parquet. So if you want to do it, use Parquet. If you actually want like a real data warehouse, like commercial one, there are things like Greenplum and Vertica and Teradata. Depending on how much money you have lots of money, buy Teradata. Otherwise, I would personally recommend Vertica. I like it, but tastes differ. So Hive, I think, was used in Facebook at some point to actually analyze like petabytes of data. And what it does is really it takes your SQL query and it compiles it to a sequence of MapReduce jobs, and then it executes them on the data. And the way data is stored on HDFS is it's partitioned on either time ranges or something else, and column values. And this way you can process each partition separately, and also maybe you don't care about all partitions. Maybe you care only about this year or previous year. So if your data is partitioned on a year or date, you can skip most of the data and just work with the most important one. And well, that's what's called HiveQL. It's basically SQL, but just with less features, and it compiles to MapReduce. And yeah, so well, this is something which was created like probably 8 years ago, so it's kind of a relatively old system, but it was used at Facebook in some time.
How much with folks like Hive or Spark is there effort needed in thinking about the initial data structures, or the, like, I understand they allow quite dynamic schemas, but then you cannot probably change it easily halfway when you discover you need something more, or let's say, I don't know, just thinking about the columns and all that kind of stuff. How much effort needs to be done before you can actually start writing these nice queries?
Yeah, so I think in general the theory is that you can just store your data and then decide how to analyze it later. Sometimes it works. The most important decision is really how you partition your data, because if you partition data wrong, you'll have to read through all the files. And if you partition it right, then, well, you can filter by these things.
Well, sometimes partitioning is also about deciding what's the record. I mean, you could put more data in a single record, or have less there. I mean, no SQL, then you could have a bigger record or something. But sometimes it might not be the best idea, or you still have to do thinking beforehand to be able to run these. It depends on what kind of queries you need to run.
So the thing is that when you have a piece of data, if you can join fast more data to this data before you write it, yeah, definitely do it, because joining it later, joins are super expensive. It's basically a reduce or a shuffle, but if at the time of producing a record you can put more fields and you can pay for the cost of storage, yeah, definitely do it. And the general idea is that like thousands of fields is fine, because they are stored separately, so if a particular query requires just 3 fields, like it will not be expensive for you. And very often, like even what happens is that people store data in JSON, and then there are tools which actually can infer schema on the fly. And well, it's definitely not the most efficient way of doing things, but at least not in terms of computing power, but maybe in terms of human power. But yeah, well, a bit of thinking helps, but also if you want to be really, really agile, then probably too much thinking is forbidden, so you have to do code first, right?
Could there, or is it common to have situations where you have data in your data store that is in, let's say, 2 different formats, like there is new data and old data that needs to do like different transformations in order to end up with the same data set? Or is that a common problem? Or?
Yeah, definitely. It's data variety. It's exactly like very often like you have data in very disparate formats, and then, well, like there are companies which actually make money by helping you transform data into unified format. And some of them actually use statistics and machine learning. But also, like if you take Spark SQL or Drill, what happens is that you can take 2 files, if they have the same field names but in different formats, then like there is no problem working with them. Obviously, if the fields names are different, then, well, somebody will have to decide how to map the fields. If it's in your head, well, perfect. But there are companies which will actually, for money, will automate this process. And you will maybe show some examples of matching fields, and then it will learn that fields with these distributions of values mean that.
How exactly this analytical queries are executed? To say I store my logs data separated by columns, and when I, for example, want to query people from location and want to know their names and age, then I just take these 3 columns, merge them into some kind of view, right? And then do it everything in memory and execute the query on it, or.
So what Spark does, it compiles really the SQL query into this computation graph, the same way that I showed you. So there is no magic. So.
Okay.
And so there is one other nice thing of columnar file formats is that you can do something called predicate pushdown. So if in your query you have some filter which cannot be used to like prune the partitions. Like for instance, you want to filter by height, but you didn't partition height. So what it can do is that when reading one partition, when decompressing the data, it can do efficiently, like removing the rows which are not important. And very fancy file formats, columnar, can actually do predicate pushdown when reading the file. And it's actually like optimizes a lot how much you have to transfer and so on. It's also very hard to do well because basically the best optimization happens when you couple your SQL execution engine to the file format, because then it can really do efficient predicate pushdown. So very often it doesn't happen, but in nice systems like Vertica and maybe Apache Drill, it actually happens quite well. So yeah. So yeah, the Spark SQL, so it's analytical SQL queries on any data source. So, well, probably if you can name it, they have it. They actually have an optimizer of queries called Catalyst. This is this logical optimizer. So they basically have a query, logical optimizer runs. It tries to reorder the joins, in which order you do them, which filters are pushed down, and so on. And then there is this physical execution plan by Spark. And then what happens is that, in general, intermediate results are compressed, again, as a columnar thing, and stored in memory. So it's something called schema RDD, and now it's called data frame, but, well, it's the same thing, really. And, yeah, so at the moment when it was introduced, like maybe 3 years ago, it was like 5 to 10 times faster than Hive, due to these all optimizations, like in-RAM computing and compression. Probably Hive people have learned from what Spark did, and this is there is something called TES, which is, or Stinger. These are these new projects which are supposed to improve Hive. So maybe, well, at some point Hive will not be worse. Maybe it's already good. Yeah, this is Spark SQL. Yeah, and here is just an example of the API. So you create you create first your RDD by reading a JSON file. You register it as a temp table, and then you just can run the query, which does something with this table. And obviously you can have many tables, you can join them, and so on. And there is also this data frame API, where essentially you do the same thing, but you just express it using, essentially object-oriented API. So data frame is really just a bunch of columns with names. And you can define a new data frame by transforming the previous one. So, well, that's what they do. So you have this data frame people, you select column age, you say it has to be less than 19, you filter by that, and then you select names. So it's really just a different view of the SQL query. And really, like, the way database people think about SQL queries is just a tree of operators. And well, first it's just a definition of what person wants. Then they can reorder these operators based on statistics, like which joins would be most efficient, which table to read first. And then it is translated to a physical plan, like, how to touch which tables at what time. Yeah, so that's how Spark SQL looks like. It's probably 3 times slower than Vertica, but Vertica is also quite expensive. It's written in C++ and by people from MIT. They are very good at what they do. But, probably currently Spark scales to larger data sets than Vertica. Although there are some rumors that there are some petabyte deployments of Vertica, but I don't know, it's a rumor. Yeah. Questions?
What common SQL features are missing in Spark SQL?
I have to admit that I don't know, but I know that Apache Drill, which is kind of competitor of this project, they claim to have most of ANSI SQL. So you can probably take your favorite business analytics tool and run it on top of Drill for sure. And with this, well, you have to try it. So, yeah.
Does it mean that instead of writing throughput, you will now write skeleton?
You can, and I would, but you don't have to. So,
Each one is interested in some particular report, numbers, it goes to write a skeleton.
well, like technically, well, that's a SQL, right? And so even with SQL, you still have to somehow send it to the database using JDBC or something. But I'm sure, like, if you take some kind of tool to run the queries, I'm pretty sure there is a JDBC interface to this thing, so you can just send SQL there, the old school way. Yeah. And so finally, Spark streaming. This is about big data velocity aspect. And so, well, like speed is in the eye of the beholder. So for some people, speed is microseconds, and for some people, milliseconds, and for some people, hours. So Spark streaming generally works at latencies of seconds. So probably, like, if you're okay with the median 1 second latency and maybe 10-second 99th percentile, then Spark streaming is for you. And you can also develop it quite fast, so like you can be productive. If you have to really optimize for latency, probably there are better systems, and if you want to be below 10 milliseconds, then you should probably use C++, not Java. And yeah, so they claim to have pretty good throughput, which in practice, what happens is that if you write a naive Spark streaming program, you will definitely not see 100,000 events per second per core, but if you really optimize it, you can get it. Like probably 10,000 events per second per core is like what you get without trying hard. And if you try hard, you can push it to 100,000. But at this level, it becomes more like a Lego set for building fighter jets. So you can build a fighter jet, but you really have to know how they work. So go figure. And well, the good thing is it scales actually to hundreds of nodes. So well, if your node has 8 cores and you have 100 nodes, well, you can do the math how many messages they can process. Again, obviously, it depends what kind of processing you do. And yeah, so one very interesting way how to think about streaming system is that you basically define a SQL query, but you define it not on the whole data history, but on the, let's say, last hour of data. And maybe you have 3 tables, which are basically 3 streams of data. And the engine has to somehow execute the SQL, like, let's say, every second on the last hour of your data on these 3 streams. And obviously, the most expensive operation is then doing joins on this 1 hour window of 2 data streams. This is actually not how Spark streaming is like formulated. Like, it has an API very similar to Spark. But logically, one way, very good way to think about streaming systems is really just SQL on like last hour of your data. And the question is how to do it fast. And yeah, so really their main selling point is productivity and the fact that it's very similar to Spark core syntax. And you can actually reuse like pieces of your Spark programs inside Spark streaming. Did anybody understand anything of what I'm saying? And questions? Yeah? Okay. Yeah. Okay, so, well, some examples of what you might want to do with streaming. So, well, the most typical case is you want to get some dashboards or some metrics with the, let's say, which update once a second, which tell you the health of your system. It can be your servers, it could be your sales funnel, it could be your ads, or you might be testing different options of your website. So what dashboards you build really depends on the context. So maybe you're getting sensor readings from your, I don't know, spaceship or turbine, and you want to see what's happening. So another case is basically some kind of real-time optimization. So you look at what's happening in the system and you tweak something. So the most simple example is there are companies which will place bids on your ads on different ad exchange networks, and you give them the budget and they will try to optimize it. And well, obviously they have to react pretty fast to events like whether people are actually clicking on your advertisement and whether they then go to your website and so on. And so, well, this is one place where streaming systems can really help. Well, if you care about optimizing online ads. But apparently everybody does. So. Yeah, event detection. So you have streams of data and you want to be notified when something happens. One interesting example is that if you have lots of lorry drivers and you have readings of speed and the level of gas in your car, you can detect when people steal gas. So very useful application in telematics. Anomaly detection is another cool word. Is basically you see your readings of the system, you learn which states are more probable and which states correspond to, well, improbable scenarios. So for instance, you get lots of readings of the parameters of your, I don't know, thousands of hard drives, and you want to predict or understand when a hard drive has failed. So you model like how the readings of the hard drive are in a normal state, and if the statistical model tells you that this state is improbable, you can say, alert, something is wrong, go check it. And well, if this anomaly detection is run on, I don't know, a turbine, you care probably much more than if it's a hard drive. So if a turbine explodes, it's bad. And to push it even further, there is something called predictive maintenance, which means that instead of detecting that something has failed, you will tell maybe one day before, by the way, probably this thing will fail tomorrow. You should probably take it offline and fix it. And apparently there are actually companies which build turbines with lots of sensors, and they have these applications which will tell you, like, I don't know, hopefully earlier than the day before, that probably you should take it offline. And apparently they charge 20% more for such turbines, so it's nice. Yeah, and any questions about that or presentation in general?
About predictive maintenance, how in general it is done? They analyze like average lifetime of components and probability of error, and then make suggestions of when some warning events get triggered.
So I would imagine that you first try to just look at the data and learn when something has failed from the data. So that's where you use anomaly detection. And then you try to use machine learning. So you know when something failed. You look at the data about the system one day before, and you try to learn basically classifier.
Patterns,
yeah.
Before coming.
So it's basically anomaly detection is unsupervised typically. You just look at the data and it tries to learn the statistical distribution of the data, which states are more probable. Probably predictive maintenance is after you can detect anomalous situations, you can try to predict them one day before, and it's supervised learning. So you create a training set, error readings one day before, but I have to admit that I could speculate about how anomaly detection works. Predictive maintenance is, like, for me, it's a buzzword. Like, I haven't done it, I don't know how it works. But yeah, also IoT, Internet of Things, it's like big data 10 years ago. Everybody wants to do it, but nobody knows what it is. So, yeah, more questions.
So there is big data and then there is no SQL. Big data is like you start with, then you have tens of terabytes or something with data, whereas no SQL might be useful in much smaller data sets as well, and many of the techniques like Spark or something, or at least the approaches. What's the overlap or not overlap between NoSQL and big data?
So my understanding of NoSQL is that 5 years ago it was NoSQL. Then 3 years ago, it was not yet SQL. And now it's not only SQL. And so what happened is that, like, first, probably what you talk about is key value stores, right? Like MongoDB, Cassandra, HBase. And obviously, they have their place. And actually, I think for scalable systems, that's a very good thing to do. Also, probably MongoDB is very productive. Like, I have some reservations about their implementation, but like, as a developer, probably it can be very efficient very fast. There are some trade-offs like consistency versus availability and how large pieces of data you can update consistently. So for instance, in HBase, you can update one row consistently. And they have some common patterns of how the data is organized on disk and what works fast and what doesn't. So for instance, in HBase, in one column family, data is organized in rows, but it's sorted by the key of the row. So you can do fast range scans. Well, that's a detail, but it's a useful detail. And well, so definitely if you want to build a large scalable system, like NoSQL key value stores can be very useful. And you probably don't want to run typical OLTP SQL queries on them. And you probably also want to export this data somewhere else and then run OLAP on them. So yeah. I also heard that there are these document-oriented databases like MongoDB and Couchbase, where you can just store your JavaScript and everything works, but I haven't much used them, and maybe I'm just too old for that stuff. I don't know. I'm not sure I answered your question. But yeah, basically what people realized is that SQL is actually useful. And so apparently also joins are useful. So it used to be that like NoSQL is like we shard the data and we never do joins between the shards. But then you discover, okay, but now I have a requirement to join the data. So what do I do? And also, very often what happens is that you build these streaming systems. So the way LinkedIn works, for instance, is that they have this Kafka, if you know, it's this message queue. And every change into transactional database is basically copied to the Kafka. I think they actually do it from transaction logs of the database. And you create full histories of your events. And then what happens, they have something called Samza, which is essentially a streaming system where you have this, well, basically a network of Samza processors. It takes in a Kafka stream, does some processing, having internal key value store, and then, well, it basically writes to multiple output queues. And you get a network of such things. And essentially, joins of such data happen via streaming in one such Samza node. And repartitioning basically means that you write to a new Kafka stream, which is partitioned on a different key. And you can very abstractly think of it as a SQL, but on large volumes of data, and so on. There's actually some very cool posts by guys who wrote Kafka and Samza. One post is called database taken inside out. So basically your Kafka event stream becomes a transaction log, and your key value stores basically become joins. Like you join data on key coming from streams. So it's very like weird way of looking at things. And it depends what you're doing. It depends on scale. So LinkedIn has a lot of data and they have to respond to it fast. Also, there are lots of consistency questions like, do you want to do exactly processing and so on. So it's a long story. Generally, people try to avoid distributed transactions and two-phase commit. Like you should really try to structure your application in a way where you can order distributed transactions in pieces which can be executed separately. Otherwise, well, the system will not scale and so on. Like, there's lots of problems. Yeah.
Can you share your common best practices for building the reports on Spark?
Reports or?
Yeah, I mean the best practice for that, how to build reports on Spark. I mean, you should data storage.
Yeah, so I think typically
just write Spark application, later on submit it to cluster, and that's all.
So typically what you do is you save data into Hive data store, and then you run Spark on the Hive data structures. So basically what Hive does is really it saves your data in files sorted by folders. That's how you accumulate your data. And then you can use different query engines to query it. One of them is HiveQ query language, which is kind of slow, but you can use Spark SQL, you can use Drill. There is also something called Impala. So it depends a bit on what you're trying to do. So Spark is a generic tool, right? You can do some machine learning, some querying, and so on. There is Impala, which is actually written in C++, and there is Drill, which is very optimized SQL engine for analytics. It's also the most freshest. There was first Impala, then Spark SQL, then Drill. So it a bit depends on the use case. It's also, I have to admit, it's all is quite young. Promises usually are true, but you have to really like massage the system to make it work. So it doesn't just work out of the box. As opposed to what they show in the demos, you actually, it's much more painful. So if you really just want to use some out-of-the-box system and you have lots of money, buy Teradata or Vertica. So it's maybe in 10 years it will not be a good decision, but probably right now, if you're a typical business application, yeah, I would consider Vertica personally. But it's not cheap. Yeah, well, I'll just tell you very briefly where I work. So our first version of the product is called Marinexplore.org, and we index various data sets about oceans. And so that you know, for instance, NOAA, which is NASA for oceans, has, I think, 40 petabytes of data or something. And of course, we don't index all of it yet, but conceptually, there is a lot of data. And so this Marinexplore.org is the first version of our system, and yeah, you can search for data, you can see some nice pictures. So here you see some sea surface temperature from some satellite. We don't own satellites, obviously, we just get the data somewhere. And there are various data sources which also produce data. And yeah, so generally you can just visualize, browse, filter, and export your data. And it was actually built pretty fast using productivity tools without maybe caring too much about this architectural astronomical issues. So it's mostly built using Python and its tool stack like NumPy and so on. We use a queue, which is a typical enterprise queue if you know RabbitMQ. So it's not Kafka. We use some libraries like DAL, which is a library for projecting data from one projection to the other, like from Mercator to Lone Ladder and so on. And we actually use these classical things like Postgres. Postgres is a geo extension for Postgres. And well, my personal favorite, Vertica. And yeah, so the next version of what we do is we try to work with different sensors and their readings. And we try to basically give a system where you can search, explore the data, visualize it, analyze it, and hopefully buy it. Also want to be a kind of integration hub because there's a huge variety of data. And it's in very different forms and very hard to access very often. And just finding the data is an issue. And yeah, we are using all these cool keywords I've been talking about. We also use Scala and Akka, if you know. Akka is this reactive platform, which also actually probably works for Java. I'm not sure how pleasant is the experience with Java, but with Scala it's pretty nice.
Maybe Akka is a good topic for next DEVCLUB or something.
Yeah, awesome.
I would really like to hear about your experience.
True, yeah.
So the Planet OS product can be considered as Marinexplore base expanded to Surface.
Well, yeah, one thing is that we really try to work with sensor readings which have X, Y, Z, and T, so spatial temporal data, and we don't really try to do too much specific for oceans or specific for seismology. I mean, we would like to be, but then we would have to be specialists in everything, like marine scientists and, I don't know, seismologists, and we're not. We are programmers mostly. We do have some people who work with meteorology and so on, but again, it's not really our core expertise. So we try to just work with spatial temporal data coming from sensors. And there's this promise that the amount of sensor data in a few years will outpace the amount of porn on the internet or something. Or, basically the amount of social data will be less than the amount of sensor data. So there are these nice exponential graphs and so on. I don't know if it works out, but we'll see. And apparently also everybody's talking about this IoT thing, which is Internet of Things. Nobody knows what it is, but it's the cool thing.
How do you make money with that? Or some government funding?
So it's a good question. We do make some money. We are not rich yet. We do want to basically build a marketplace where the different companies which compute or collect the data can sell it. And there are many companies which actually do that. There are companies which do surveys, like some company wants to do something in the ocean or on the land. So there are companies which do surveys, and well, we could be the intermediary. There's also the issue that, again, there are satellite companies, lots of satellite companies, which is again exploding field, which produce lots of data, and they don't have very good data management tools. And obviously, if you have access to data, you can provide customized analytics for a specific customer. And so it's a combination of many things. But the entry point is basically data search. So you can search data by spatial temporal parameters, keywords, metadata, and so on. And even that is often a problem. There is huge amounts of data, even free data, which is produced by American taxpayers. And nobody can find it because it sits somewhere in some weird folders with weird names. And if you're very persistent, you'll probably track it down. But there is no good way of finding them. Very often people just have lists of hundreds of bookmarks. So the way you did research in the 90s, you create a text file and you put links and you follow them. And that's how it works in this domain.
So in terms of the technology stack, the OS is not at all overlapping with Marinexplore.
We do reuse some parts. So we do run Python for things we want to. And actually there's PySpark, right? So you can run, basically Spark is wrapped into Python, and you can really write Python code the same way as Scala code. So, and in principle you can even reuse some C++ components of Python libraries and just call them for these RDDs and so on.
What was the reason for you to choose Scala over Python for the next project? Was it performance issues or scalability issues?
It's a good question. So Python is a very good tool if you just have to do something fast. It's probably not very good tool for programming at scale. It can probably be compensated by very, very good culture. You write lots of unit tests and integration tests and everything. But I think at some point, at least at the interfaces, static typing is nice. That's my personal opinion. But I know people who write in Clojure with big systems. So Clojure is this dynamically typed Lisp on JVM. So it's another cool thing which people in San Francisco do.
There is Datomic, another product which is built by the same people with Clojure. Do you have any experience or comments on that?
Let's say I heard about it. If I had to decide right now whether I should use it, I wouldn't. But I have to admit I haven't really studied it very much. So it's a very niche thing. I think Clojure, in my personal opinion, it's a very interesting language. But it will stay niche because it requires certain. So basically, if you have a very large brain and you can use half of this brain on maintaining your Clojure program, and you can use the other half for doing useful stuff. So if your brain is a bit smaller like mine, then maybe you can just use 1/3 of your brain for. That's my opinion. But very smart people can do very cool stuff with Clojure and Haskell and so on. So if you feel your brain is big enough, then definitely go for it.
Great talk. I know you've been